Hi, today we're going to talk about polyprotic acids. The word polyprotic means having many protons. And so basically these are acids that have more than one H plus that can go into solution. So basically what we're working towards in this video is calculating equilibria with polyprotic acids. So I'm going to start by talking about possibly the most important polyprotic acid, because this is what controls what we call carbonate chemistry in the natural world. We have a lot of CO2 in our atmosphere, and if that dissolves in water, it forms carbonic acid. Carbonic acid is a weak acid, and so it can dissociate a proton to form H plus and the bicarbonate ion, HCO3-. But that HCO3- ion still has an H on it that can dissociate, and so that dissociates into H plus and the carbonate ion, CO3-2-. We'll come back to this in a little bit. For a diprotic acid, because there are two protons that can dissociate, we have two dissociation reactions going on, and therefore we're going to have two equilibrium constants. The first equilibrium constant we are going to call Ka1, and that is the Ka setup for the acid losing the first of its protons to form its first conjugate base, Ha-. Then it has a second equilibrium constant, Ka2, which is based on the dissociation of the second proton to form the second conjugate base, A2-. So back to our carbonate chemistry, the first proton dissociation reaction has a pKa of 6.35, so that means the Ka is 10 to the minus 6.35. The second proton dissociation reaction will have a pKa of 10.33. So although acids can have many protons, in fact I can think of some that have up to 6 protons that can dissociate, most of what we're going to be doing here today is working with diprotic acids, the sorts that have 2 protons to dissociate. And so let's talk about calculating pH for a diprotic acid. So if you measure the pH of a solution at equilibrium and use that to calculate the H plus concentration, that H plus concentration came from 2 different sources. We have some H plus that came from the dissociation of the completely protonated acid, H2A, and then we have some H plus that came from the dissociation of Ha-. But if you go through and you look at the Ka values for a whole bunch of polyprotic acid, what you're going to see is there are usually several orders of magnitude between the first Ka and the second Ka. What does that mean? Well, it means that you're going to get many more products of the first dissociation than from the second dissociation. So when we look at our equation for how much H plus we have at equilibrium, we can assume that the H plus concentration from that second ionization is really, really tiny, and we're just going to ignore it. So we're going to make a simplification here, and we're actually going to make 2 of them, but the first simplification we're going to make is that our H plus concentration at equilibrium is going to approximately be the H plus concentration that we get from the first ionization. So as far as pH goes, and H plus concentration, this acid is more or less behaving like a monoprotic acid. Now we're going to take that simplification and set it aside for a while. We'll come back to it later. Now we're going to talk about calculating the Ha- concentration. And why this is tricky is that we have 2 different dissociation reactions going on, and in the first one you're creating Ha- from your H2A, but in the second one you're destroying the Ha- by turning it into A2-. So we can write an overall equation for how much Ha- we have, where the Ha- concentration we have at equilibrium is the amount that we get out of the first ionization minus the amount that's destroyed in the second ionization. But again, think back to our Ka1 versus our Ka2. This is going to be a really small amount compared to how much is created by the Ka1 reaction, and so we're going to ignore it. And so our second simplification is that the Ha minus concentration at equilibrium is approximately equal to what is created in the first ionization. Now let's go back to our two reactions by looking at the first dissociation reaction and taking into account the fact that the H plus concentration is behaving as though the second reaction does not exist. The Ha minus concentration is behaving as though the second reaction does not exist. We can sort of pretend that second reaction does not exist for a little bit. And then how are the concentrations of H plus and Ha minus related to each other? Well, we're making 1 mole of H plus for every mole of Ha minus. So the H plus and the Ha minus concentrations must be the same. So let's look at our expression for Ka2, and you see it's got an Ha minus in the denominator. Well, Ha minus concentration is about equal to H plus. So we can write it this way. And then, hey, those H pluses are going to cancel. And then what we get is that A2 minus concentration is going to basically be around the same value as your Ka2. So when we go to calculate equilibrium concentrations for diprotic acids, we are looking to calculate 4 different concentrations: the H2A, fully protonated acid, the Ha minus, the acid that's lost 1 proton, A2 minus, that's lost 2 protons, and then the H plus concentration. So we're going to assume that the A2 minus concentration is approximately equal to the Ka2 concentration, and then we're going to figure out the remaining concentrations by assuming that the H2A, Ha minus, and H plus just behave the way a monoprotic acid would. So here's a problem in which we're looking at ascorbic acid, also known as vitamin C, and we're going to use these rules. So here are the concentrations we want to calculate. The first thing is we're going to assume A2 minus equals the Ka2. So there's our Ka2 value. Let's put that down here. Our A2 minus concentration is going to be 1.6 times 10 to the minus 12. Now the next step is to calculate the remaining concentrations by treating them as a monoprotic acid, which is basically the sorts of acids we've been calculating up till now. So what do we do when we calculate concentrations in a monoprotic acid? We use an ice table for starters. So here is our ice table. I've put in the starting concentration, the 0.32 molar for ascorbic acid, the H2A, and then 0 for the Ha minus and the H plus. And then we start putting in our changes. H plus concentration change is always going to be plus X. And then the other two changes are linked by stoichiometry. Use those to calculate equilibrium concentrations. And, let's make the assumption that H2A is approximately equal to 0.32. So now we're going to take those equilibrium concentrations, we're going to plug them into the expression for Ka1, and set that equal to the Ka1 value we're given in the problem. And then we could solve for x squared. I got x squared equals 2.56 times 10 to the minus 5th. Taking the square root of that, I got x equals 5.1 times 10 to the minus 3rd. So what does that mean? Well, x happens to be the H plus concentration, so that gives us our H plus concentration. X is also equal to the Ha minus concentration, and then H2A is approximately equal to 0.32. So now we have all our concentrations, and all in all, the math was not too bad. So mostly when we deal with diprotic acids at this level, we're basically using shortcuts. Are there ways to calculate all these concentrations? Yes, there are. And maybe if you take my advanced environmental/analytical chemistry class, you will learn how to do that. But for the most part, these approximations work pretty well. So we're going to stick with a simple method for now. And as someone who's done, more detailed calculations on these simplifications actually work pretty well. So I hope this was helpful, and I will see you again soon.